Hello everyone, I'm Theo, your quantum group professor. So today we'll start the actual quantum groups, lecture number 2, compact and discrete quantum groups. For those maybe who didn't attend the first lecture, so don't leave. The first lecture was about operator algebras. We learned a lot of theory there, but here we'll just need the so-called Gelfand theorem. It's not that complicated, and I'll recall that in the beginning. Also, for those who came right here, didn't attend the first lecture, so what's the plan? Lecture 1 was operator algebras, now lecture 2, the basic definitions, compact and discrete. Then we'll have 2 lectures, 3 and 4, on the basic theory developed by Voronovich, representation theory, Harmeasure, Tanaka, Peter Weil, basic stuff in the middle. And then lectures 5 and 6, more advanced. Okay, so a bit of an introduction to research. Well, this is very recent, it's 30 years old, so recent and very hot and interesting. So let's find this presentation first. Here we go. So compact and discrete quantum groups, as I was telling you. So this is a theory which was developed by Voronovich in the late 80s, which means it's quite recent. I mean, many things to be done here. We've been working on this for 30 years, but there are still many things to be done. So what we learned today, definition of compact quantum groups, definition of discrete quantum groups, also basic example of such beasts and operations on them. And finally, we'll do some quantum isometries. Why this? Because in the first lecture, we talked a lot about non-commutative spheres and tori, and the tori's actually will show up quite naturally in relation to these quantum groups. For the spheres, you have to work a bit to consider quantum isometries of these spheres, the three ones that we introduced in the previous lecture, and show that all this is compatible. So, okay, it's basically definitions, basic things. Then a lot of examples and operations that will be the main thing that we'll do today, actually, the bulk of the lecture. And then finally we'll show that everything is compatible with what we did last time. I mean, these three spheres, they have quantum isometries, which are quantum groups in our sense. And then next lectures, as I was telling you, Harmeasure representations of somehow heavier theory. This is just an introduction today, okay? So here we go. Oh yeah, some preliminaries first, operator algebras. What was the idea? So you have system algebras of norm involution. Basic examples are algebras of operator on a Hilbert space for closed algebras. And the GNS theorem states that actually these axioms here are very simplified. Mean exactly that your algebra is an operator algebra. In finite dimensions, you get some direct sums of matrix algebras. That's not very complicated. And the main theorem, which is important for us, is the Gelfand one, which states the following things. So you take such a sister algebra, I mean, complex algebra with norm involution, must be a Banach space, of course, and with this tricky condition over there, A star is A to the square in norm. In the commutative case, these are exactly the algebras of functions on compact spaces. So why is this true? So let's review this in 2 seconds. If I take a compact space, the functions on it, continuous with values in C, form a sister algebra because you have the subnorm on it, the involution, just put your bar, and that formula over there is just a triviality. I mean, at the sub point is just ZZ bar is Z to the square in absolute value. So definitely C of X is a sister algebra. Now in the other sense, how do you reconstruct X out of C of X? You take the characters, right? These are the Dirac masses at the points of X. That's the proof of Gelfand. I mean, you have the spectrum of A, which is the space of characters. That's how you define it. You have a morphism from A to C of X. And then, well, you have to work a bit and do some spectral theory somehow and get to the results. Spectral theory means, you see, these algebras are actually algebras of operators. So these operators are just some infinite matrices. So somehow the tools here for sister algebras come from the fact that, from usual linear algebra that you know very well, just extend it to infinite dimensions. It's a bit tricky, but it works. And with this kind of tools, you can prove the Gelfand theorem. Now, Gelfand is very important for us because when you see this, you say, okay, in general now, if A is no longer commutative, I'll just write it like this and call X a non-commutative compact space. And as basic examples, you have the group duals, for instance, can be considered non-commutative tori somehow in this theory. Also, you can construct free spheres and a lot of other beasts. I had some fun last time in doing this. And the following question was left, yeah, what about groups? Or what are the non-commutative analogs of the groups? And first thing is that you don't call them non-commutative. That's the terminology. You call them quantum, okay? So it's non-commutative spheres, non-commutative tori, but quantum groups. That's it, okay? So this is how it works, the terminology. And okay, so let's see what these quantum groups are. Here we go, so beginning. In order to understand what a quantum group is, let's look a bit at the classical groups, okay? We need to know that, of course, very well. So let's take a compact Lie group. Lie means, I mean, it's C infinity, but in practice, it's a manifold, smooth manifold. In practice now, it's known, and it's not trivial actually, that such a compact Lie group is a closed subgroup of a unitary group. So finally, we can actually, yeah, maybe forget about compact Lie. Let's just take a closed subgroup of a unitary group. So that's how the interesting groups appear actually. Orthogonal, unitary, symplectic, permutation, superoctahedral, right? Anything is there. So yeah, this will be our objects of study, compact subgroups of UN, very good groups. And it's actually kind of difficult to come out with something not of this type. Well, GLN, of course. Okay, let's not get into this. Very good class of groups. Now, what's the multiplication? Well, this is no longer an abstract thing. I mean, the compact Lie grouping in the beginning is something abstract. Now we're into concrete things with the matrices. So that's your multiplication, of course, the dumb formula for the matrices. Now, let's look at the algebra. We're interested in the algebra of functions. So C of G by Stone-Weierstrass is generated by these coordinates, right? And why? Because these coordinates simply they separate the points. So very good. So C of G is generated by these guys. So now let's try to understand how this multiplication works in this functional analysis setting. So the point is that multiplication goes from G cross G to G. Now, if we look at algebra of functions, we have an arrow from C of G to C of G cross G, which means C of G tensor C of G. Okay, so what we're trying to understand now is how this map maps Uij. So Uij should be sent into some kind of tensor. Well, and the tensor we get it from the formula, the upper formula. Just put the same thing as before, but instead of capital U, capital V, you put these U things, and you put a tensor here in the middle. Okay, that's the magic of tensors. I mean, well, you have to think a bit at it, but that's it. These tensors are just magic. So you just take the multiplication formula, put the tensor here in the middle, and that's your transpose. I'll be back to this. So, well, very nice. So C of G, just the algebra generated by the coordinates, and the multiplication of the group somehow at the dual level is just this very simple formula. So we're done with classical groups. We have a very good understanding of the compact groups of matrices in terms of the algebras of functions. Well, now we're ready to go for quantum groups. So we'll do exactly the same thing as here, but we'll no longer assume that C of G is commutative, right? So here are the axioms, which are due to Voronovich 87, a bit modified here, but these are the good axioms. We take a sister algebra with a unitary matrix whose transpose is unitary too. That's what's called a biunitary matrix, whose entries generate A, such that we have maps like this. So delta, this is the formula that we had before, right over here, bottom. And then, well, this is somehow the multiplication, somehow of your quantum group. Now, you also need something for the unit and the inverse, right? And these are the so-called co-units. This maps epsilon over here and the antipode S over here. If so is this case, we have these things which are satisfied, our algebra A with our matrix U, satisfying these three things. We write a C of G and also C star of gamma actually, and we'll call G a compact quantum group and gamma a discrete quantum group. So all this, well, it's very simple. It basically comes from here, but it's gonna need some time to be understood. So I'll have like 8-10 slides about comments on all this. But now let's just maybe even without understanding well, well, it doesn't look that bad. I mean, it's a simple definition of K. It's very, very similar to what was happening here in the classical case. Finding a compactly group, rather the algebra of functions on it, is something generated by the entry of a unitary matrix with a delta map like this. And if you want to be very correct, the group of course has a unit and inverse, and it also this epsilon and this maps. So it's yeah, it's exactly the same thing. You just assume that your algebra is no longer commutative. Now there are a few subtleties, of course. So let's see what could be a bit strange at the first sight. Yeah, the biunitarity condition. So for matrices, unitary implies you transpose unitary. You know, well, in the setting when the entry is non-commutative, this is no longer true. So that's why you have to assume that U is biunitary. Okay, that's a subtlety. Now here everything is fine. Yeah, why opposite here for the antipode? So you see for C of G, what we're having before, if you look at the inverse, or whatever at the map involving your algebra A C of G, it doesn't matter if you put there algebra or opposite algebra. But for more complicated examples like discrete duals, non-commutative tori, things like that, you really need the opposite. So yeah, that's something to be remembered. You have that opposite sign there, and we'll see in a few slides in a few minutes why this is really needed. Now here, yeah, of course, C of G compact quantum group, because it's just this, but without commutativity. Regarding the second thing, so our claim here is that we have at the same time the definition for compact and discrete. And this, we'll get back to it a bit later. But the idea is that we've seen in lecture 1, I mean, compact is dual to discrete, it's somehow the same thing. So that's it. I mean, yeah, okay. Assuming that you have all the compact quantum groups, and we kind of have them, it's clear that this will work. We have also all the discrete quantum groups appearing as duals. So all this will be explained now. Just one more comment. So Voronovich did all this, but he was using more general axioms. And more precisely antipode, you see here, it's an evolution. I mean, what you're doing on the coordinates, you flip the indices, another star. So if you do it twice, indices will get flipped twice, the star will appear twice, or it will appear. So S square is the identity in the setting. Voronovich did things with the S square more arbitrary, and here we won't be interested in this for a number of reasons, and among them is that Voronovich was 87 at the time. It was very interesting. The main examples of quantum groups were like this, with this square different from identity. 30 years have passed and water has flown through rivers on Earth since, and many examples have been constructed in this setting of ours. The square is equals the identity. So now we are in 2020. Now we have so many interesting examples satisfying these axioms over here. The square of the antipode is the identity, including quantum permutations, quantum reflection groups, Q deformation as -1, all kinds of these, which are very interesting. So these are the good modern axioms. Okay, no need to further complicate things. Okay, so this was for the philosophy. Now let's get to work. So we need to understand a bit first why this is really true. Okay, AC of G with G compact quantum group, also the discrete thing, and then to see how to understand these objects. So compact groups. For a closed group, the algebra C of G with standard coordinates satisfies the axioms. The structural map delta epsilon S are just the transposes of multiplication with inverse. That's something that we already know, right? So this discussion was about this. And conversely, any commutative Voronov algebra. So Voronov algebra is the algebra A, okay? So A is Voronov, G is a compact, gamma is the discrete quantum group. So any commutative appears in this way. So this we basically know. Let's see what's here in the slides. Yeah, some computations here. Yeah, it's a justification. So I told you before, when we did this, there is the magic of tensors without more explanations. Well, here is the precise explanation. So if you compute MT, you get this, and you get your tensor. Okay, so that's we have now the full proof. No bullshit. Now, also I told you about unit and inverse, and you believe me, I hope. Well, here is now the complete proof. The transpose of the unit is this, so it's exactly your epsilon. The transpose of the inverse is exactly uij, uj star. That was the formula for the antipodes. So we're fine. Conversely, so you take a commutative algebra satisfying these axioms over here by Gelfand is C of x, but this x has this C of x has delta epsilon s, so this means that x itself, the space, has a multiplication inverse unit, so it's a group, and you're done. Okay, so I proved this. Very good. So classical case understood. Now let's go to group duals. So I take a discrete group with n generators and finitely generated. Then the group algebra with the diagonal matrix formed by the generators satisfy the axioms, and the maps once again are something very simple. So G goes to G tensor G. This is your epsilon, this is your inverse. Now, in analogy about the commutative case, now I have to characterize these things. We'll prove this in a second. So the second thing is that this algebra is co-commutative in the sense that delta is invariant under the flip. You can see that flip G tensor G, same thing. But this is something clear, so we just proved it here. The converse is true, but this is more complicated. We'll see it in lecture 3. This is representation theory. So proof now. Yeah, so yeah, we have to construct morphisms like this. So well, it's clear. I mean, they come from group representations, okay? So delta, yeah, just take this unitary group representation. So this is gives you a map like this, okay, by linearizing. C star gamma is the linear combination of things of gamma. So same formula. Epsilon can only come from the trivial representation, also again by linearizing, and the antipode from the inverse linearized. So we're done. By the way, remark here that G goes to G minus 1 is a representation, but going from gamma to the opposite of C star gamma. Because why? GH minus 1 is H minus 1, G minus 1, so it won't work. I mean, it's not a representation, the inverse. It's a representation, but with values in the opposite algebra. So that's why the opposite algebra is needed here in the axioms here, okay? Opposite is needed. In the classical case, doesn't change anything. For in the commutative case, can put A or A op is the same, but for group duals, you really need this A op. So getting back maybe to this, yeah, we are here on the axioms. So very good. These are the axioms. Definitely, you cannot change anything. It will destroy the axioms. This op stays here, and of course we can write this. I mean, we know in the commutative case it's exactly the compact groups. So definitely we have compact quantum groups, and we have these discrete things too. So very good. Now. Yeah, some comments now. Let's go now into this Pontryagin duality. So when gamma is abelian, that's something that we know. C star of gamma is C of G, with G being the dual. Now, the problem is that this was something valid for C star algebras, okay? Proof was by Gelfand. C star gamma is commutative, by Gelfand must be C of G. G is a group of characters, and that's your Pontryagin dual. Now, these algebras are Voronov algebras, okay? They have delta epsilon s, so you have to check somehow that delta epsilon s on the left, as we define them for group duals, equal delta epsilon s on the right. So be more precise, these guys coincide with these guys, we had this on isomorphism. Well, of course it works. And you can check it, it's a few lines and it works. So this means that G is gamma hat, the thing that we had the last time in lecture 1, as spaces somehow, as non-commutative spaces, is a quantum group isomorphism. So yeah, once again, things find a duality. So motivated by this, whenever we have, so I told you, whenever we have a Voronov algebra, write it as C of G star of gamma, and we'll say that G gamma are dual to each other. I write these formulas. And because why? These things that we've seen here, it's exactly an extension of Pontryagin duality. So very good. Third comment now. So remember in the classical case, these are actually compact Lie groups. So I forgot a bit about Lie in all this. That the compact case actually we have a smooth manifold structure. So well, in general now we don't have. That's the problem with quantum groups. They don't have differential geometry, no Lie algebra in this setting. But we'll see later that with a lot of algebra like representation theory, Tanaka duality, easiness, other things, you can go to the same level as in the algebras, no problem. So that's not an issue, the fact that we don't have geometry. However, you have from time to time a bit of it, geometry. So for instance, given C of G, a Voronov algebra, you can take the star algebra generated by the coordinates Uij. Well, we'll call this C infinity of G because in the classical case, that's what you get, the C infinity functions, smooth functions. Let's see, even without geometry, we can do some definitions. For instance, this algebra, which will appear all the time in what follows many times, is, yeah, we can denote it if we want C infinity of G without even knowing what, well, C infinity means, but yeah, just a notation, okay? As an example, yeah, for group algebras, you get group system algebras, you get the usual group algebra. Now, one more comment. So you see, for group algebras, there was this problem vaguely discussed when we did operator algebras, is that C star of gamma is the universal algebra, but the image of C star gamma in the regular representation, it's called the reduced algebra, is also group algebra, and they are not the same. I mean, depends on gamma. If gamma is so-called non-amenable, like a free group or something, these guys might not be equal, and that's a problem somehow with Gelfand duality. Going back to sister algebra, so you have two sister algebras giving somehow the same non-commutative space, gamma hats. So that's a bug with Gelfand. Okay, it's a bug. We should say things out there. It's a bug. So time to fix now this bug in our setting here. So I agree to identify Voronov algebras when the smooth functions of algebras of functions are isomorphic, mapping coordinates to coordinates. So why this is good? Because this identifies, for instance, group, full and reduced group algebras. In the classical case, of course, nothing will happen because there's no analysis there. Well, let's not get into this, but that's the definition that we will use, and it's good. It fixes this bug of Gelfand functoriality. Okay, summary now. Time for a summary. So these are our axioms. Pairs AU with morphisms like this. We have compact and discrete quantum groups in this way, just a notation. All this notation is motivated by our results that we had. In particular, these quantum groups are dual to each other. So we have a Pontryagin duality well understood. Finally, we use this identification. So identify two quantum groups if the star algebra of coordinates are equal, and all this is supported by many things. Okay, Gelfand and that we did so far. Now, as a technology in order to deal with this beast, so well, we have delta epsilon s, right? That's what we have for the moment. So let's study a bit these guys. So they have these properties called co-associativity, commutativity, co-universality, which are clear. I mean, just check on generators, and you're done. Now, where do these things come from and their names? Because in the commutative case, remember delta epsilon s were the transposes of multiplication unit inverse. Now, multiplication unit inverse satisfy the group axioms, which are like this, right? Multiplication is associative, the unit is the units, and the inversion satisfies this. Well, this is somehow notation for GG minus 1 is 1. So what I'm doing here, so delta is the diagonal thing. So I apply this to G, okay? Let's try to understand this. So I want to say that GG minus 1 is 1 in a complicated way, okay? So delta of G is GG. Now E tensor I, this means I'll get to the pair GG minus 1. Then I apply M, I multiply. So this is G times G minus 1. And yeah, that's the identity. So the point is that when writing the group's axioms in this way, if you want to transpose them to see what delta epsilon s satisfy, well, you just put tensor everywhere, right? That's the magic of tensor. So that's how these three formulas, just by putting tensor there, finally we reach to these things here. Okay, so yeah, there's a bit of a tricky thing here. I mean, the proof of this is just trivial. You verify these formulas from the coordinates, and then you're done by linearity multiplicativity. But there's a tricky thing, however, that in the classical case, yeah, these are exactly the group axioms. Now, so getting back to our summary, so we have all this as before, and we have some tools now. Delta epsilon s satisfying this. So whenever the idea is you want to do something with quantum groups, go back to this delta epsilon s and build on these three formulas that you have, which you find is exactly as groups. I mean, when you want to do groups, at least at the very basic level, what you have is multiplication unit inverse, right? So build on that. So we're exactly in the same situation. So very good. Yeah, we have the good tech for dealing with these guys. Let's get to some examples. We haven't seen any examples so far because besides the basic ones like groups, duals. So first of all, we have products. I'm sure relax a bit. That's gonna be more easy. So first, given two compact quantum with GH, I can define the product like this. You see, I'm just tensoring the Voronovich algebras. That's Voronovich algebra done. So I call it product. At the dual level, let's try to understand what happens if we do this. So if you tensor two group algebras, you get the group algebra of the product. So very simple operation, the product, but as an application, so you can take products of classical groups with group duals. And you get in this way something which is not a group nor a group dual. So finally, it's quite interesting, the product. These are our first examples, which are not groups and not group duals. Just pick your any group, different from one, of course, any group dual different from one, make the product that's a quantum group. I mean, it's not something known. Now, let's also have free products. So there's a bit of an issue here. Let's do it first at the dual level, actually. So if you take a free product of group algebras, of course, you'll get the group algebra of the free product. So that's your free product notion for the discrete quantum groups, okay? Now, in the compact case, we'll get something a bit weird. I mean, we can once again, taking these algebras, which are now commutative in the classical case, okay, I'm assuming that we're classical, get something non-commutative, so that's definitely not the free product. It's a so-called dual free products quantum group. So these were just some remarks. So now we start again. Dual free products are no arbitrary compact quantum groups. Then we can define something that we call dual free product, not free product because it's not just like this. You take free product of Voronovich algebras. Of course, there are some matrices here. Them diagonally like this, U and V here. The matrix is there, and this is a quantum group called dual free product. At the level of the associated discrete quantum groups, we use just the star notation because it's a free product. Okay, so a bit subtle here. Actually, the inventor of these things, Su Wang, actually messed up the definition. He called them free products. Well, anyway, that's the modern notation and terminology. And this is interesting too because we plug in anything, you get, for instance, non-classical groups, or yeah, you plug in anything different from 1 and 1, and you'll get something non-classical. So very interesting things. Free complexification now. So that's also a bit tricky. So actually, yeah, let's start to the classical case. So if you want to pass from UN to UN, that's no easy business, because you either needs how unitary matrix decomposes in terms of diagonal of orthogonal matrices was clear. So best is to do it with Lie algebras, right? Say that somehow the Lie algebra of UN appears as a complexification of the one of ON, and then the groups themselves appear as the compact form exponentiation. So yeah, it's not very simple to say that UN is a complexification or ON is not easy business. In the free case, we'll see that actually the free orthogonal unitary quantum groups are related by a very simple operation, and that's the one free complexification. So let's see how this operation works, and we'll get back later to these free quantum groups. So given G quantum group, we have the matrix U there. So I'll just multiply by Z, which is unitary free from it, okay? That's what I'm doing here. The unitary, it lives over the circle, right? That's your generic unitary. I'm taking a free product of the C of the circle, the C of G, and inside I have both U of U. I multiply them. I call this U tilde, and I take then the Hist algebra generated by the entities of U tilde. So that's Hist algebra with U tilde. I'll call it C of G tilde. It's a kind of free complexification, of course. Okay, all the coordinates multiplied by a free unitary. Now, as usual, let's try to understand what happens if we do this at the dual level. So, well, it's exactly the same thing. We use the same tilde, but here, here we were saying that C of T, the generic unitary, lives on T. Now, since we're discrete here, it's better to say that this is C star of Z. It's the same thing, right, by Pontryagin. It's the same thing, but just, it's better with C star of Z in this setting. So we'll be back later to this. It's very interesting, as I told you. No subgroups. Well, simplest here is just try. So you take G compact quantum group and an ideal, and you divide. The problem is delta must factorize, right? Also epsilon s, but especially delta. So if you want delta to be factorized, you're led into this condition of so-called ideal condition. So that's the result. Okay, take quantum group, close ideal satisfying this condition, and it works. You have a quotient. Now, at the dual level, well, these things we have Pontryagin duality. So whenever you have a duality, arrows go in the other sense, okay? But its inclusion becomes surjection and vice versa. So H subset G dually would mean that you have a quotient of discrete quantum groups. So very nice. This notion is very straightforward. If you ever forget the Hopf ideal condition, just try to prove it. If delta factorizes, for delta to factorize, you need this. So yeah, it's not very complicated. No quotients, of course. So for quotient, actually, we need the notion of co-representation. So this is something that we'll study later, but we need them here just for this construction, their definition. So that's just a matrix which satisfies the same. These are exactly the conditions for U. Okay, it's a U. Of course, it's a kind of representation of our quantum group and dimensional. So that's your definition for general representations of a quantum group, which are called co-representation of the algebra. Okay, that's the rule in quantum groups. When you pass from the compact quantum group to the algebra and vice versa, you add or remove a co. Never forget that co for not messing up things. Okay. So now if you have this co-representation, well, you have a quotient group. This will generate something. An algebra inside C of G, you call that C of H. That's your quotients. Dually, as I was saying, things go in the other sense, so you get a subgroup. Very nice. 6 now. Wow. So a lot of operations. So projective version now. Yeah, that's interesting. So it's a quotient operation. Okay. So for quotient, I remind you, need a co-representation. You take this guy here, which is the so-called adjoint co-representation. There's nothing mysterious about it. It's just in double indices, and that's what happens in the classical case where you take an adjoint representation. the dimension doubles. I mean, and it's best to do it in double indices. In our case, well, it's clear that it's a co-representation. Just write delta epsilon as we get it into seconds. And so I get the quotients quantum group, which is called PG, projective version. In the classical case, that's the usual projective version. I guess most of you are familiar with this, so you model G by the what's inside of the diagonal. For the group duals, now let's see what we get. Well, the fundamental representation of this diagonal matrix for my GI. So now what I have here, finally, I won't have really double indices. I must be equal to J and A to B in order for a thing to be non-zero. So what I get here is, and on the right, I get GI minus 1. That's exactly what I wrote here. So very good summary again. So we have this theory, and now we have these 6 operations: products, dual free products, free complexification, subgroup quotients, projective versions. So this looks very, very good. That there's a bug somehow. I mean, as basic input for all these things, we only have groups and group dual so far. Okay, we don't have anything. So you're somehow into a closed circle finally of ideas. If you use these 6 operations, which are of course can lead you to very complicated things, but it would be better now that we have our operation to have also a bigger input. So for this, yeah, let's talk about free quantum groups. These are interesting due to Suzu Wang some 25 years ago. So I take the sister algebra generated by the entries of an orthogonal matrix. That's what's written here. So self-adjoint entries, transposes the inverse. And that's your quantum group ON plus. Same thing in a unitary case. We must assume that U is biunitary. Have a universal algebra there. That's your UN plus. So, well, first you have to prove that this works. I mean, that these things are indeed Voronov algebras. So you have to construct delta epsilon s. And for this, well, basically for delta, you have to map Uij into these guys, right? So finally, you have to prove that its matrix U delta satisfies the conditions here. That's all. And same for epsilon s. Let's just talk about delta. But this is clear because, for instance, for ON plus, if U is orthogonal, then this matrix here is orthogonal to its orthogonal computation. So you have your delta. Same for epsilon, same for s, and same in the unitary case. So it works. We have quantum groups. And as a first remark, of course, these are bigger than ON plus, UN plus, because ON plus, UN plus is the same thing, but assuming that the coordinate commutes. So these are new things. And they're not products. I mean, look at this list that we are having here. What we're doing there is not a product or a subgroup quotient, whatever. So it's something new. It's called liberation. Now, let's see a bit what are the properties of these quantum groups. So, first of all, UN plus, it's exactly the biggest one, okay? Just in the classical case, UN is the biggest among its subgroups. Here is the same. So, why is this true? Well, this is just the biunitary condition of the axioms of Voronov, which were stating that having an n by n quantum group, you need an algebra generated by a biunitary with maps and so on. So it's a quotient of this algebra, right? So the Voronov algebras n times n are quotients of C of UN plus. This means that the corresponding quantum groups are subgroups of UN plus. So that's our number one here. Well, in the orthogonal case, I mean, if you want your quantum groups to be orthogonal, you means U bar, you get into ON plus. Of course, you have embeddings, ON plus, UN plus. This follows from 1, 2, actually. But these are obtained by dividing by the commutator ideals, if you want. These are what we call liberations. Why? Well, because of these formulas here. I mean, if you add the commutative here and here, assume the coordinates commutes, then you'll get exactly UN. That follows from Gelman, for instance. Okay, so yeah, these quantum groups, I mean, they have the same properties as ONUN in the classical case. And now, yeah, the problem is, are these really new? I mean, maybe they're not. So I have to check that all these inclusions are proper, okay? ON into N plus and UN into UN plus. And you think a bit that it's, yeah, I mean, actually that's something we already know, have already these operations. So I already told you that with these operations, you can construct weird quantum groups that are not classical nor group duals. So this must live here inside UN plus. So UN plus is definitely different from UN. And if you look, well, if you're more careful now, you take the same constructions, but you keep all the time things real, you get also this inclusion is not an isomorphism. So it's something that we already know this theorem, but let's prove it directly because it's interesting, the proof, the simplest proof somehow. Is to look, let's just look at the diagonal subgroups. So, I mean, the group dual subgroups, remember, the group duals, they come with this diagonal matrix, right? So, of generators. So here, what we can we put, what's the biggest thing that we can put inside UN plus? So, of course, the dual of the free group, right? Right, generators. That's the biggest group dual. So, of course, it lives inside UN plus. Okay, now in the classical case, of course, this one works. So you have to assume that your coordinates G1, Gn of your group dual are real. So you're led to this this group here, Z2 free product itself and times. So as you finally these things which appear on the diagonal, the biggest group dual subgroups are here, dual of Fn, dual of Ln. Here, of course, you get the torus and the cube. So they're all different. Well, it's just a proof. I mean, we already know this from product operations, but why this proof is interesting because you see you have here exactly the tori we were talking about the last time. So if you look at these diagonal things, group duals, so you have here is a cube, torus. So the dual of this is what we're calling free cube. The dual of this is what we're calling the free torus. So not only we prove this theorem, but we have a connection with the free tori, and that's very nice. Okay, so all this is compatible with the free tracing that we did last time. Well, finally, once you have it, you can look for more, like for intermediate liberations. So you see, if I start now on the right with the free versions, how do things on the left appear? By assuming that AB is BA, the coordinates. So now, why not putting something weaker than AB is BA? So let's try with this, ABC is CBA, the so-called half commutation relations. And the result is that you get indeed your half liberations here. Well, proof as before, I mean, you want to, for constructing delta epsilon s, you need to check that these three matrices satisfy the new relations that you added. So the half commutation, this is just clear. I mean, there's no need to compute. If the entries half commute, so do the entries of these guys here. So you have your delta epsilon s defactorized. So very good. More can be said here. What can be said more? Yeah, of course. So in analogy, for instance, the inclusions are proper. You just look at the group dual subgroups inside, and of course, for these guys, you can do better than classical, but worse than free, right? At the group level. So there are proper inclusions. That's pretty much it, because yeah, so far our theory is just definition and checking that things are proper. So that's what we have. Very beautiful theory. At the moment, we'll see later. Okay, in another lecture you can liberate basically anything, also permutations, reflections, many other things. But for a beginning, it's a good thing. So we have liberations of ONUN, also have liberations. Now, yeah, maybe one thing. So we've seen that there is a connection with free tori, so we have some non-commutative geometry which is developing. Okay, had last time free spheres, tori, and now these quantum groups. Quantum groups are related to the tori, so let's see now if the spheres are. There is also a relation. In this way, we will get everything very, very round like this. Well, for the moment, very small, but which can evolve afterwards into some kind of non-commutative geometry. So that's an exercise that we have to solve now. Are the spheres and these quantum groups really related, the free ones? So for this, of course, in the classical case, how do you get the quantum group, the group from the sphere? Well, it's the rotations of the sphere, right? The real sphere, the isometric group is UN, and in complex, well, it's UN. So I need to talk about isometries now. And isometries are of many kinds. I mean, these are, you can do them affine. You are in a Riemannian sense. Here we'll just look at the dumb thing. I mean, affine, very simple. So we just say that in the classical case, given an algebraic manifold of the sphere, because we want everything to be inside the spheres, just take the unitary matrices which fix the manifolds. That's the affine isometric group of X. Okay, so there's no metric anything, there's algebraic manifolds here, algebraic geometry, very basic. And for the spheres, of course, you obtain ON and UN. Now, quantum will do exactly the same thing. So given an algebraic manifold here in the free sphere, meaning that it comes from some polynomial relations, we take all the quantum groups acting on it in the sense that you have such a coaction map like this. And well, if you do a bit of algebra, there is not difficult. You see that there is a universal object in this category, and that's your quantum affine isometric group, denoted G plus of X. Okay, so classical is G of X, and quantum isometric group is G plus of X. X, it's bigger. So theorem now, and this is what we're looking for, so relation between spheres and quantum groups. So yeah, the quantum isometric groups of the spheres are these guys here. The spheres being, of course, those that we know, classical free. The ones in the middle, well, they are recent, so we have to introduce them. You just take the free spheres and you assume that the coordinates are subject to ABC, CBA. Okay, so that's your definition. So this is well defined, and the quantum isometric groups, if you compute them, you get these guys over here. Let's see how the proof goes. Well, first of all, you have to do many things. So first, yeah, let's go back. Let's prove first that UN plus acts indeed on the free sphere. And then we'll go back and go towards the rest of the diagram. That's going to be easy. So let's prove that UN plus acts on the sphere. So for this, we must construct a coaction map. Let's go back to the coaction. So we must map each coordinate to these guys here. So finally, we want to prove that these guys here satisfy the relations for the coordinates of the free sphere. So sum of A, UIA, XA. Sum of A, UIA, XA, same thing. Let's call it capital XI. And now we verify the relations for the sphere. Sum of this is 1, sum of this is 1. I'm using here the fact that you use binary type. So we get an action. Now, if you have actions, so this act on this, now you have to prove that one plus acts on this sphere and so on, so on, so on. But it's just by imposing some extra relations. So if you assume that your RG are real, or half commute or combinations of this, so we'll do these variables there, xi. So we're done, we have actions everywhere. Okay, now, well, last thing to prove is that the actions are universal. And this is, well, it's a bit tricky, but you can get it. Actually, it's not that. In the free case, it's trivial because there's nothing bigger than UN plus, right? Or N plus if you're in the real case. So in the free case, we're done. So we can say that we're happy with this. In the free case, we're done. That was our main purpose here. In the classical case, this is that's the result. Did that first, Bhumik and Goswami. Just write down this formula here and then apply the antipodes. That's the only trick. Apply the antipode and I'll see you get it. And in the middle, well, it's a bit more technical, but anyway, for the moment, it's a bit anecdotal, this half liberations, just for saying that we have more examples. So we won't really need this at least for the moment. So done with this. Okay, conclusion. So we did a lot of things today. So we have axioms, very simple, beautiful axioms for these algebras, which are at the same time for compact and for discrete. Now I ever need to something else. The duality formulas are very well understood. All these Monteagudo things we're talking about, very well understood. No ever needs any extra theory here. As our tool, we have manipulations with delta epsilon s, which is pretty good. It's like group theory at the very basic level. That's what we're doing here too. We have our operations. Many examples, and that was the whole point of the presentation. 6 operations, liberation of liberation. So very good. And all this is compatible with the tori and the spheres. So that's important. With the tori, you look at this diagram, like this group to all subgroups. And with the spheres, we have this quantum isometry. So all this looks very good. So what's the weakness in all this? Definitely axioms, no. No one will ever change them. The duality formulas, yeah, that's done. And closed business. Manipulations are our main tool, yeah, that's obviously the weak point because groups, if you're there with the multiplication unit anyways, you won't get that far. So you need more theory there, like representations or Lie groups or the algebras or whatever other techniques. So 3 is our weakness. Many examples. Well, that's pretty decent what we have. But of course, if you look at this, how we constructed liberations or half liberations, it's clear that this works for many other groups. So it's not really a weakness, but just something which is not complete. Okay, so by spending some time, more time on these things, we definitely can come up with more examples. So that's just something to be worked out. It's quite routine. Compatibility, yeah, done. So the weakness is 3. We need techniques. As I told you, there's no, yeah, we'll do representation theory. There's no differential geometry, just forget. No, don't even try to construct a algebra for these guys. We won't be able to do it. So we'll have representations here, and that will evolve into Tanaka duality, which will evolve into something called easiness. I mean, we'll build here something very, very heavy, a bit like in algebraic geometry. You start with cubics, and then you have manifolds, and then ideals, whatever schemes. So you can, it's going to be this kind of philosophy, okay? Building things more and more abstract and powerful. So that's going to be starting from the next lecture, okay? This was lecture 2, and lecture 3, 4 will be about representation theory, and then lecture 5 more, 6 more specialized. Okay, guys, hope that you like it, and see you soon for another lesson.